This program is a presentation of UCTV for educational and non-commercial use only. Check out our YouTube original channel, UCTV Prime, at youtube.com/UCTV Prime. Subscribe today to get new programs every week.
Good afternoon. I'm William Lester of the Chemistry Department and Chair of the Hitchcock Committee. On behalf of the Graduate Council of the Academic Senate, it is my very great pleasure to welcome you today to the second of the two Hitchcock lectures to be given by Professor Harold Kroto. The Hitchcock Endowment Fund was established from a bequest made by Dr. Charles M. Hitchcock in 1885 to institute a professorship at the University of California, quote, for free lectures upon scientific and practical subjects, but not for the advantage of any religious sect, nor upon political subjects. Through a generous bequest from his daughter, Mrs. Lily Hitchcock Coit, the Hitchcock Endowment Fund was enlarged considerably in 1930, allowing the university to liberalize the terms of professorship and to extend the period of residence of its holders. The fund has become one of the most cherished endowments of the University of California, sustaining and encouraging recognition of the highest distinction in scholarly thought and achievement. Harold Kroto was born in 1939 in Wiesbach, Cambridgeshire. Did I pronounce that correctly?
No, I'm pronouncing it correctly.
I see. And was raised in Bolton, Lancashire. He graduated in chemistry at the University of Sheffield in 1961, and in 1964 received his PhD there for research with R.N. Dixon on high-resolution electronic spectra of free radicals produced by flash photolysis. He started his academic career at the University of Sussex, Brighton, in 1967, where he became a professor in 1985, and in 1991 he was made a Royal Society research professor. Professor Kroto's research program at Sussex has covered several interdisciplinary areas. One area focused on the creation and spectroscopic characterization of new molecules, in particular unstable species and reaction intermediates which contained labile multiple bonds. This work led to the production of the first molecules with carbon-phosphorus double bonds, as well as the development of the first analogs with carbon-phosphorus triple bonds. Since these pioneering studies, the presently extremely active field of phosphoalkene and phosphoalkyne chemistry has developed. Laboratory synthetic and spectroscopic work on cyanopolyenes led to the surprising discovery by radioastronomy that very long carbon chain molecules were relatively abundant in interstellar space. During a period which explored the possible source of these carbon chains in space, laboratory experiments which simulated the chemical reactions in the shells of red giant carbon stars were carried out, which serendipitously discovered the existence of C60, Buckminsterfullerene. In 1996, the Nobel Prize in Chemistry was awarded to Professor Kroto, along with Professor Richard Smalley and Professor Robert Curl of Rice University, for their discovery of this previously unknown class of carbon molecule, in which 60 carbon atoms are linked in the form of a soccer ball. These and similar molecules were dubbed fullerenes, or Buckyballs, after the discovery in 1985, because their geodesic molecular structures are suggestive of the architectural domes designed by R. Buckminsterfullerene. Since then, chemists have synthesized some 5,000 variants of the buckyball, including elongated spheroids, sheets of carbon, and microscopic tubes. These tubes are believed to have greater tensile strength than anything yet made, and that they will conduct electricity as well as metal implies that the potential uses are tremendous. These presently active research areas derive directly from the earlier work on C60 and focus on the implications of the discovery for several areas of fundamental chemistry, as well as the way in which it has revolutionized our perspective on carbon-based materials. Without further delay, I am pleased to present to you Professor Kroto, whose lecture topic today is C60, Buckminsterfullerene, not just a pretty molecule. Professor Kroto.
I hope you can hear me. I'm glad to see someone's come back after yesterday's lecture. You never know. Maybe you weren't here at yesterday's lecture. That's why you're here today. You never know. It's a pleasure to give this second talk. And with a bit of luck, I'll be able to get the slides moving. And it's a pleasure to see Professor Towns in the audience, because he's responsible for some part of it, which is the astrophysical part. So we'll come to part of that as we go on a little bit later. It's a curious story because I think, as I discussed yesterday, you never know, I never knew which way I was going to go in science, and this story for me starts really out in space with the first slide. Have the lights down, and the first slide. Here we go. This is a spiral galaxy, and I think it's one of the most beautiful and symmetric spirals I've ever seen, and I don't think anyone could be anything other than captivated by it. We're looking at 10 to the 11 stars or so, and the galaxy is rather similar to our own, the Milky Way. And as we look across the galaxy, say if we consider our own sun somewhere out here in the doghouse, basically wide out in the spiral arm, as we look across the galaxy, we descend to see various objects such as these hot clouds of gas. Now, the hot stars heat the gas to incandescence, and basically, if we look at stars and look at the spectra, what we find in these, and particularly in the gas clouds, they're full of hydrogen. If you look a little more detailed, you find that other elements are there. All the elements, oxygen, nitrogen, and hydrogen, etc., are there. If we look at some other objects, such as stars, such as this, we see an interesting phenomenon that the outer shell has been blown off. That sort of star is rather important in this particular story. In fact, this sort of star is rather important in your story. Every carbon atom in your body was produced in a star somewhat similar to this. Hydrogen is squeezed to helium. 4 protons squeezed into helium. 3 helium nuclei squeezed into carbon. Every single carbon atom in your body was once in a star like this. And then the star blew up and blew your carbon atoms out into space. And then these carbon atoms wafted around and ended up in the biosphere as you. Now, you're therefore rather lucky, because your carbon atoms could still be out there. And in fact, there are certain people I can think of who I think should still be actually out there. But anyway, unfortunately, some of them came. Now, let's go on, because these stars are interesting because physicists tend to look at them. But there are some black areas, such as these, which are smeared across the galactic plane. And, well, physicists tend to look at the bright things, chemists at these black areas, because in this, chemistry goes on. And these black areas were known to the Greeks. They looked at the sky and saw these black holes, and they thought that these were holes in the celestial sphere. Celestial sphere was a dish, a glass dish, and the stars were diamonds stuck in this glass dish. The glass dish was supported by Arnold Schwarzenegger, and a sort of Scottish football supporter had heaved a brick through the glass dish, and that's where these holes were. And we now know that that's not a correct picture. We know it was an English football supporter that actually threw the brick, actually. But in fact, these areas are very interesting because they harbor... The microphone is on.
It's up, it's low right here. Hold on, and on like this. It's in there, okay.
Yeah, it's on, eh?
Okay.
It's on me. It's on electricity, but it's on here. All right. Now then, I'll just, I'm sorry you could not hear me, but modern electronics will win in the end. It's this area that I think was opened up by Professor Townes around the 67, 68 with a really fantastic discovery that these black clouds were actually full of molecules. The first one, ammonia and water, and then other things. The usual thing that you add to water is alcohol. That was in there too. And from other molecules, as we shall see, were in there. Okay, so how did this affect my story? Well, it started in a really rather interesting way because my colleague, David Walton, was an expert at stringing carbon chain molecules together. If I have the lights on for a second, I hope you can just see this. I think it's important to realize that the start of this story for me was quantum mechanics. As a long carbon chain molecule vibrates and rotates at the same time, there's some interesting interaction, and I was interested in the molecular dynamics of this, and you study this through what's called microwave spectroscopy. And so that was the start. Dave had these fantastically long carbon chain molecules, and we got together with an undergraduate. An undergraduate synthesized one of these to look at the vibration rotation behavior. And this is one of the 8 carbon atom molecules, but David made one with 24 and 32. But we started off very simply with one with 5 carbon atoms, and it's the one up here. Now, it had 5 carbon atoms, and by microwave spectroscopy, we could study it and get its bond lengths. This was about the same time that Townes and others had opened up this Pandora's box of molecules. And in fact, the molecule that interested me then was this one, because that was there. And if this was there, the question was this guy there? It only had an extra 2 carbon atoms, but it looked like a long shot. And I contacted Takeshi Oka, who was a colleague of mine, fantastic scientist now at the University of Chicago. And we got together to study this and see whether we could detect the molecule in space. Well, here was the particular signal. Here we see HC3N with 3 carbon atoms. We see SO2 and formaldehyde. In Sagittarius B2, it's very strong. In Orion, the carbon chain molecules are rather weak. So we focused on Sagittarius and used this particular telescope. Now, to give you an idea of one of these telescopes, this door up here is big enough to walk through. And in fact, if you're expert, there's a winch up the top where you winch up the amplifiers up to this prime focus. And if your experiment isn't going on very well, you can always hang yourself from the end of here, or throw yourself off if you can't tie the rope well enough and fall down. And I tell you, when you do astronomy, most of the time it doesn't work. So there are quite a lot of astronomers are hanging on there and falling down. This is Canada in the middle of summer, actually. So, you know, it's in Algonquin Park. And this is the telescope we used. And we were absolutely delighted to discover that this molecule was actually there. Here is the set of rotational levels, and I hope you can see this, but then anyway, this is the signal for HC5N, and this is the signal for HC3N. And we were absolutely delighted because then that was the biggest molecule, heaviest molecule that had ever been detected in space. Well, then Dave and I got together, and Dave managed to work out how to make a molecule with 7 carbon atoms. And so there's some real chemistry involved with this, and Colin Kirby worked with us to make this molecule. And I was excited because I was going to go to Canada to use the telescope, and the day I left, Colin had only got to here. And every time he got to this second step, all he got was coal, because, you know, a lot of carbon in there. So I sort of went off to Canada and went out to the telescope, and we started to do some work out there. And then got a contact, because it turned out that Colin managed to get this spectrum. Now, this sort of spectrum, it may not look very nice, but to a microwave spectroscopist, this is like the centerfold, right? This is beautiful stuff. You may think it's 3 porcupines trying to cross Shattuck, but in fact, it's a rotational spectrum of this molecule. It's absolutely sensational. Lots of vibrational structure. These are rotational levels and beautiful vibrational structure. This is what I'd been interested in doing. However, Colin managed to get the spectrum, work out the frequencies. He phoned my wife, and she wrote the numbers on an envelope, and I thought I'd show you this historical envelope. Here we see Simplicity Style 6613. Well, that isn't it, actually. That's a dress. If we'd focused on that, we might have found dresses. It turns out it was on the other side of the envelope, which is shown here. It was the B value of cyanotriacetylene, and if I just focus on this, it just gives you an idea, hopefully. Not a very good spectrum, but good enough to get those numbers. And she phoned a colleague, Fokker Kreutzberg, in Ottawa, and he phoned out the telescope, and that was on a Saturday morning. And 1 hour beforehand, Takeshi Oko, with brilliant timing, had arrived just in time. See, I'd been there for 3 or 4 days, basically, but Takeshi, a fantastic scientist as he was, came just at the right moment. We got the number, went out to telescope, and then I think one of the most exciting days of my life occurred, because we didn't have all the electronics you have today. We could only store 10 minutes integration at a time. And so we did statistics on whether the central channel was high or low. In fact, it would have been boring with modern electronics. You know, you don't realize when you do research, you youngsters today with all this electronics, how exciting it used to be. And hard. Okay. Well, anyway, we looked at 10-minute integrations. We were doing statistics, Takeshi and I, saying that central channel is high or low. And by about midnight, we decided that, you know, it was high statistically more often than it was low. And we were so excited. And then we stopped the whole run and, in fact, integrated it all up. And we found this wonderful signal here. And the central channel there is high. It was in there. That was the signal for HC7N. I've never actually had a more exciting day in the whole of my life. And one might think it was C60, but it was quite different. It was this one. And then we went on, and later on we were able to detect another molecule, and we show here HC9N. And the question was, why were these carbon chains floating around in space? I mean, you don't see them walking around San Francisco. You know, these carbon chain molecules are not so obvious. You have to make them. So there's some reason that these clouds are full of carbon. The question was, what was it? Well, it's certainly true that I just thought, well, I think they must be coming out of stars. And one reason was that, you know, it's very difficult to synthesize those molecules in interstellar space. There just aren't really enough collisions. So the question really was, if you look at this black cloud here as a bit of map, you can't see it very well, but there's only a little bit of a spot. Just if you see these two stars, about here is a little deep well of carbon. And I thought maybe an old carbon star was hidden in there and produced these molecules. Well, this is the picture that we have of the way the sun was formed out of these clouds of gas. The black clouds condense and then heat up. A star forms, such as the sun. And our sun is about 5,000 million years old, somewhere about here. In another 5,000 million years, it'll blow up into a red giant. It'll solve the energy crisis and one or two other crises as well. But anyway, we're only about halfway there. And then it will blow a lot of material back into space. So the picture was, were these shells of gas full of carbon? And a wonderful star was detected, IRC 10216, which had a shell which was blowing out and had a lot of these carbon chain molecules. And Rich Sakeley, I think, was involved in some of these. He's in the audience, and is really the culprit for getting me here, probably as much as anybody else. He usually gets me to do his freshman lecture courses, but this time he's got me to do this one as well. Anyway, this star is beautiful because it's full of carbon, blowing material out into space. And as luck would have it, one day I was visiting Rice University. I was visiting Bob Curl, a microwave spectroscopist friend of mine, and he said I should go and visit Rick Smalley, because Rick had developed this fantastic apparatus which could vaporize essentially anything. And there are some of, anything. Okay, so I was at Rice and visited. And here is the heart of this apparatus. On the left is a solenoid valve which opens and shuts, and helium passes down this 1 millimeter channel. When it gets to about here, you fire a laser which vaporizes material, and on this disc was a silicon carbide, and it was blown out into a vacuum at this point. And in that, you could actually put, say, iron on here and produce a cluster of iron with maybe 20 or 30 iron atoms. And I wondered whether it might be possible to use this and vaporize graphite. Well, let's have a look at the apparatus in a bit more detail, because here is the valve, opens and shuts, and the plasma of material that comes out of here passes along to this point, and at this point it goes through a skimmer, and when it arrives at this point we have two plates which are charged. You fire a second laser, which ionizes whatever's in the beam, and suddenly, as they're ionized, they're flicked up this tube. The heavy guys go slowly, the light guys go fast, and so by time of arrival, you can determine the mass of what is coming up this particular time of flight tube. So the idea was, if you put carbon in here, maybe the plasma coming out of this which is shown here, the plasma coming out and going through the skimmer, might be similar to the plasma coming out of a star. Now, this is a planetary nebula, but somewhat similar. We see a plasma around this particular star. If it had a lot of carbon in it, maybe this would simulate the conditions in that sort of star. So I suggested it to Bob Curl, and Bob said he would work on Rick to actually do this, and in something like the late summer of 1985, I got a phone call to come to Rice University. We're going to do this experiment, and so I rushed. I got a ticket on Continental, and I got there in 3 days, to Houston. Now, the first two guys I met were two fantastic students. On the right is Sean O'Brien, on the left is Jim Heath, who was at Berkeley for some time with Rich Sakeley, and is now really doing fantastically well at UCLA. You can see we're doing really good research, eating chicken fajitas, Budweiser and Coors. This was at our favorite Mexican restaurant, as we'll see. And there was also Yuan Liu, who's now back in the States. And these students really knew how to run this apparatus. It was like, a 747. I could just sit with my feet up, looking at the video screen, and students would do all the magic. And as we worked on it, the good news is we saw the carbon chains. No problem at all. The bad news was there was an interloper. Something else was there, and it's shown here. On the 4th of September 1985, on this particular printout, we got this fantastic picture. Let me take you through it. This says in microseconds, 20 microseconds. This is a cluster of carbon which took 20 microseconds to get from the bottom of the tower to the top. These took longer, so these are heavier. This is C10, C11, C13 is here, 14, 15, 11, 15, 19, and 23 are strong. There's something interesting about 11, 15, 19, 23. We're still not quite sure what it is. What we didn't know, and no one had noticed before, that there's something really unbelievable about C60. And I wrote C60 plus question mark. Wednesday the 4th, repeat this, C60 huge, C70 also. And I wasn't the only one, because when we looked in the student's logbook, one thing about Rick's group, you write it up, And there was, on the same day, C60 and C70 are very strong. The next day, C60 is very large. What was it? What was so special about a cluster of 60 carbon atoms? Well, this is what the textbook says. The textbook says that graphite should be this, and here there are about 60 carbon atoms there. So you'd think, look at the textbook and say, well, is it this thing? Is it some sandwich, roast beef sandwich of graphite? It's not easy to explain, but there are some interesting structures with 60 atoms. So the question is, what's going on? Well, I thought I'd show you the floor of Bob Curl's loo. This is the washroom. Now, every morning I would sit and contemplate this floor. What's so special about it? Here we see the number 6. And if we put 6 hexagons round there, we get 24. Well, you can sit there forever, and you can contemplate forever, but you will never see the number 60. There will no, and the question is, what are you doing? You're looking for symmetries. You're looking for some pattern. You're looking for something special about it. So it's not there. So the question is what to do. It doesn't seem to solve the problem. Well, when you've got a problem in science, the thing to do is to go for lunch. And at lunch, we were sitting at a particular table, shown here, And they cleared away all the paper that we were drawing on. But it turned out underneath this table there was a beautiful solution, which is shown here. But it had a few too many carbon atoms. Now, in these days of political correctness, I must point out that you must not assume you know the sex of the person wearing these stockings. We Brits have everything covered. I mean, you know, including that. Anyway, we're sitting there deciding what the solution was to this, and that wasn't it. And we're sitting there discussing it. And one thing I remembered, that for my children, I made a model of the sky. It's a star dome, and it's I call it a star dome, but it's actually a map of the sky on a truncated icosahedron. I was telling, you know, Rick, I've got something. It's got a load of hexagons. It's probably got somewhere like 60 vertices, but it's also got pentagons as well. It'd been so long before that I just couldn't remember. And I was thinking, should I call my wife up? And looking at the time, it was looking like 2 or 3 o'clock in the morning. But the other thing is that we'd also discussed the fact that Buckminster-Fuller seemed to have solved this problem. Now, I hope you can see this. This is actually a fantastic photograph of the Expo Dome in 1967, lit from the inside. And you'll see that, I hope you can see this, but it's actually a load of hexagons. It's rather like the floor. So somehow, Buckminster-Fuller had curved this into a closed cage. And if you could make a closed cage out of this, this would explain why this molecule was rather stable. So anyway, that night, Rick played around with hexagons, and then he remembered that we discussed the pentagons, and when he put pentagons, something very interesting happened. The whole thing started to curve up into a ball. And the next morning, he came in with this beautiful model here, which had 60 vertices. It is the truncated icosahedron, has the same shape, and at that moment we just bowled over. It was just fantastic, and so too beautiful to be wrong. I remember thinking, it doesn't matter whether it's wrong anyway, it's so beautiful everybody would love it. And then about a few weeks later, cold fusion turned up, and everybody loved that until they realized that was wrong, and so I decided that maybe be a bit more circumspect about it. But anyway, we decided it was so good that we would publish it, and we wrote the paper up. That was our Tuesday morning, and I think we sent the paper off on the Wednesday afternoon. That was the fastest paper I've ever been involved with. And then suddenly we discovered it was a soccer ball. And that was a surprise. You know, this molecule, we've been kicking around in Rick's apparatus, and people have been kicking the damn thing around football pitches for quite a long time. So that was very, very interesting. Not only was it probably carbon, but it was also a soccer ball. And one of the reasons that it was stable is that you need 12 pentagons to close. It's not an accident that the soccer ball has 12 pentagons. One here, 1, 2, 3, 4, 5, and 5 below, and then one on the other end. And 5 times 12 is 60. And if you add that, which is required from Euler's law for closure, you can't do it with hexagons, to the fact that you need to have pentagons isolated for chemical stability, in those two factors lies the answer to the structure of C60. Well, the second thing is what to call it, and we decided that we'd call it after Buckminster-Fuller. I managed to convince Rick and Bob that this was a good name. There was a bit of a discussion because, you know, it's a longish name, Buckminsterfullerene, and it's not too easy to say if you're Japanese. But it turns out that they gave in partly because they realized that if they didn't, you'd be stuck with the real UPAC name, which is this one. I think this tells you something about UPAC and those who like to quantify. I mean, you know, if you ever try to get a generalized name for anything, that is really quite something. So anyway, we decided that Buckminsterfullerene would be a good name. Well, the question now was, how can you prove it to be right? Because we had just a whisper in a helium wind. And the beautiful chemist's experiment would be to get the NMR spectrum. All 60 atoms of fullerene 60 are equivalent, and therefore the carbon-13 NMR spectrum should consist of a single line. Now, so I had this dream for about 4 or 5 years to see a single line. You see, I'd done something that E.B. Wilson said you shouldn't do as a microwaver. I'd actually been involved and certainly published papers on the basis of single line for the first carbon-phosphorus double bond and for the assignment of HC5N in interstellar space, and the single line spectrum, mass spectrum of C60. So I was rather keen to show that it was C60 by a single line and a mass spectrum, and show it to my friends who, they had half a dozen carbon atoms, they had 3 million lines, to show you could do it with a single line. And I thought some smart young organic chemist would actually do it first. Anyway, let's see what we did. We didn't have lasers, so we thought, let's do something rather simple and use a carbon arc. So when I got back to Sussex, we set up a carbon arc with carbon rods here, and we made a mistake. I mean, I thought there would be very little C60 produced by this, and we sputtered the material onto an electron microscope slide. And here is Jonathan Hare, a key student in the second part of my story, adjusting the carbon arc. Here's a bell jar. And we found that the structure of the carbon arc changed between 60 microns and 95 microns. And I thought that maybe that signifies the point where C60 was being formed, and I would need a mass spectrometer to see it. That was a mistake. I thought there would be maybe 1 part in a million of this material would be C60, but in fact it's about 5 to 10%. So I'd been sitting with it. I was sitting on this for a year or two trying to get a mass spectrometer, and was unsuccessful. Then one day, I got this letter from an astronomer, Mike Dura at UCLA, and he said, "Harry, presented at Capri, do you believe this?" Exclamation mark, Mike. And it was a paper by Kretschmer, Fosteropoulos, and Huffman. Search for the UV and infrared spectra of C60 in laboratory-produced carbon dust. And the answer is I couldn't believe it. Because in that paper, there was an infrared spectrum with 4 infrared peaks. Now, I think this paper should stand as one of the greatest historical papers in modern chemistry, because we knew then that the vibrational spectrum of C60 would have 4 vibrational peaks. As a violin has 6, and a violin has 4, and a guitar has 6, C60 has 4 infrared active peaks, and there they were. I looked at this and said, well, for this to be true, there had to be between 1 and 5% C60. It was impossible to believe this. And they were physicists anyway. How could physicists get this right? Okay, impossible. However, it was the start of the year, and it was an impossible experiment, and we have undergraduates work in the laboratory, and the thing to do with undergraduates is to give them an impossible experiment, in my view. I mean, there's no point giving them an experiment that works, because then they come to do PhDs thinking research is easy, No point that. You give them a hard experiment. That's my belief. Anyway, it turns out that what you give them experiments you're really interested in, and usually they're much more speculative and actually much more imaginative than the ones that you tend to do with a postdoc, because postdoc has to get a job and you're much more conservative. Anyway, I gave this. I said, look, check this out. What the hell's going on here? And here on the left is Jonathan Hare and Amit Sarkar, who was at the Island School in Hong Kong. There's someone here, so one of your mates from your school. And they pulled out this again. In fact, if you saw the NOVA program, this is the apparatus that these 2 guys brought out, and I thought that Jonathan was the star of that program. And we just looked at it, and blow me down, but they did see these peaks. Not very strong, but this was just sodium chloride and the teaching lab infrared spectrometer. It was very, very surprising. What could this be? Then, show you the notebook, Jonathan's notebook. Came back from Scotland to find the FAB mass spectrum had been done with exciting results. There was a 720 mass signal. It was really, really exciting, but still impossible to believe. Could it be possible that when you're watching Charlie Chaplin in those old movies and through a carbon arc, okay, it had been producing C60 all the time? That's what this was telling us. Then here, I think the single most important experiment done in my laboratory. Jonathan, on a Friday, added about 25 mils of benzene to this material that was sputtered off. to stock mixture and allowed to stand for the weekend. The reason was that we thought, well, if it is C60 in there, was it a gas? Was it a solid? Was it soluble? We discussed whether it might be soluble or not several times. But Jonathan really believed that he had it, because here we see C60b. That was our shorthand for C60 Buckminsterfullerene. And Jonathan went in, did this experiment, and on the Monday, he put this on my desk. A little red sample tube with a red solution, and it was staggering because this was graphite. Graphite doesn't dissolve. Diamond doesn't dissolve. And if you were washing up and your diamond dissolved, you'd be pretty pissed off. And the person who bought it would be even more pissed off, I think. And so there you go. Could this be it? It was very, very hard to believe. And now it looks ridiculously simple and straightforward, but then it was very, very difficult to believe that this was it through this very simple method. So I was looking at that, and in fact we see Jonathan's logbook. It looks slightly reddish. On the Thursday, on the 9th, evaporated down to 4 or 5 drops. The fab showed no C60. That was a very difficult experiment. We now know that would have taken another few days to work that one out. Anyway, that was on a Thursday. The next day, on the Friday, I got a call from Nature, and that's the journal. And I never know why people laugh at that. I mean, anyway, so whatever. Anyway, so Philip Ball asked me, would I referee this paper by Kretschmer? Had they, because they'd got another paper, and I said, well, I knew something. And now let me say something. You never see the hurricane coming. I said, sure, I know something about this. And then came, the next day, came this fax. Solid C60 in new form of carbon by Kretschmer, Lamb, Fosteropoulos, and Huffman. 12:05, Friday the 10th. It was a bad day. I read this paper, and it was a red solution. And not only that, there were crystals. Beautiful crystals. This is one of the great photographs, scientific photographs of the 20th century. It is crystalline carbon, which crystallized from an organic solvent. And not only that, there's an X-ray structure. Even the right way around, it actually is right. This was C60. So I'm sitting and thinking about this. It's 12 o'clock. And I'm thinking, this is bad news. I'm sitting with a red solution on my desk, mass spectrum, thinking, shall I commit suicide? I'll go for lunch. And, I don't know what universities are like in this country, but in Britain, going to lunch at a university is roughly the same as committing suicide. So I thought I'd just try the prolonged agony. And so I went for lunch, and I read the paper, and I decided this was the most fantastic paper. Rang up Philip Ball and said, look, you've got to accept this paper immediately, because I knew this paper was going to be on the desks, 20 more desks within the next day. It was such a wonderful paper. And I think that Kretschmer and Huffman, fantastic guys, did a wonderful piece of work. And there's no doubt in my mind that their contribution was up with ours, but unfortunately the prize only goes to 3 people, and also the students were heavily involved in this, but that's the way this thing goes. But this was a wonderful piece of work. Anyway, the question what to do, and I read the paper through, and I thought, well, there's a little bit left to cling on to, because they did crystallography. Now, the really sweet experiment for a chemist was the NMR. Was it a one-line solution? And I was sitting next to my colleague Roger Taylor let me just focus that a bit, in the coffee room, and he said he would help us, and he grabbed all the material we had, and he discovered that if you chromatograph this red solution, it's split into 2. On the left, a magenta solution, on the right, a red one. And we sent them down to Tony Avent in the NMR room, and Tony rang, I said, hey, you better come, I've got a fantastic one-line spectrum for you. So we rushed down, and there was this wonderful one-line spectrum. Gee, don't clap. He said, don't get excited. He said, this is benzene. He said, that's been done. I've just checked it up. It was Faraday extracted it from fish oil in 1826, and Philip Ball says you're a bit late if you want to publish that in Nature, right? Anyway, he said, but look, he said, if you get to take this magnifying glass and you look here, he said, I reckon that's C60. And that is the historical one line, that miserable little, but to me, very beautiful signal. I love it because that's the first NMR signal of C60, one line. And Roger went back, rechromatographed it, got a beautiful separation. On the top is C60, and on the bottom is the icing on the cake because it's C70. And C70 is very interesting because you take two halves of C60 apart. You can split, say, a soccer ball into two halves and put 10 more carbon atoms around the waist, and you get C70. And it should have 5 different types of carbon atom, and therefore 5 lines: A type, B, C, D, and E type. So we not only had C60, we had C70 as well. So that was really very, very exciting, and in a sense is the story up to 1990. From 1985 to 1990, all that was going on, and as I say, the first paper was with Rick Bob, Sean O'Brien, and Jim Heath, who was here, and as I say now at UCLA. Kretschmer, Huffman, Lamb, and Fosteropoulos, the second paper. And that's how I think the field was born. And it was not born by trying to go after C60. Our work was, the experiment itself was to try and understand the chemistry in a carbon star. Rick's view was that it was cluster science, because he was coming from cluster science, that wonderful technology for getting clusters. Kretschmer and Huffman, it's very interesting. They were interested in the dark patches in space and the light that came through it. They were interested in carbon dust in space. And they had seen a spectrum, a UV spectrum of C60 in 1983, before we discovered C60, and they had a brainwave. I think one of the most brilliant brainwaves that anyone has ever had. Kretschmer and Huffman thought, maybe this UV spectrum that we've seen in carbon dust is C60. It was an unbelievable piece of, I think, scientific detective work. And every time I look at their work, and the more I look at them, the greater admiration I have for it. And it should be the archetypal example of the way infrared spectroscopy can be used to identify molecules. It is the one thing that works. It is fingerprinting of the highest sort of exactness, and also of historical importance. From group theory, you can determine that there are 4 infrared active vibrations, and it was crucial to the discovery of the way to extract C60. Well, let's go on, because let's see whether we got some lessons to learn. The first is that the molecule was thought of before. In 1966, David Jones, in The New Scientist, under the name of Della, said, "There is a curious discontinuity between the density of gases and that of liquids and solids. Della has been contemplating ways of bridging this gap and has conceived the hollow molecule. This would be a closed spherical shell of a sheet polymer like graphite, whose basic molecule is a flat sheet of carbon atoms bonded hexagonally, rather like chicken wire. He proposes to modify the high-temperature synthesis of graphite by introducing suitable ill-fitting foreign atoms or molecular units into the sheets. His idea was to somehow introduce pentagons into the hexagonal sheet and make it close up. Not only that, something that I'm sure many of you can read here is this from 1970 in Japan. Eiji Osawa, and with his supervisor in 1971, Yoshida, published this. And here we see at the bottom, I hope you can see it's a bit small, but it's C60, had thought of this molecule and had said if you could make it, it would be stable. So here was an imaginative piece of Japanese science which no one took any notice of. Maybe 1 or 2 people did. Orville Chapman at UCLA tried to make it, and maybe independently. And in fact, I've been trying to check back whether anyone had thought of it previously, but this seems to be the first publication of the concept of C60 itself. Well, what lessons? The first is we should have known. Here's a virus, and we see hexagonal packing, and on the corners we see pentagons, and it's got 12 corners, 12 pentagons required for closure. If we look at this Orlonia, we see essentially the Buckminsterfullerene dome. Here we see hexagons, but this little guy knew that it could not close without pentagons, and there we see a pentagon. And we find that that is a fundamental law that no one can actually break if you want closure. One of my favorites is this. Here we see the shell, and we see hexagons here, and at the front and at the back we see pentagons. And if there were not a pentagon here at the back, it would have a flat shell, and it'd be bloody drafty up the backside, I tell you. So there you go. These guys know it. Another one is a favorite, is Jeff Goldblum was working in our lab for one time, and he got stuck in the apparatus, and when he came out, he came out looking like this. And it's interesting that we see that here we have hexagons, but you see these pentagons, that the segmented eye of this particular fly is fascinating because it has soccer ball eyes. It comes from Australia. In the work of Piero Della Francesca, we see this beautiful drawing of an icosahedron, and also, of course, as I showed yesterday, icosahedron absciscus vacuus, the hollow structure, hollow by Leonardo da Vinci. So, if you don't like Buckminsterfullerene, maybe you should call it Leonardo da Vinci, which is even longer. Well, let's look at Buckminsterfuller's dome, because it's a very interesting structure. If we see it, we see that here we have a hexagon, and it's triangulated. And you need the triangulation, because the triangle is a rigid structure. All other structures are not. If you make a square, it can become a parallelogram. And it's a double skin. We see, in fact, there's an inner skin of hexagons, which is what you saw when the light was on the inside. So with a structure like this, you can actually cover the whole of Los Angeles or San Francisco. One day we might just have to do that. And in fact, here we see there is a pentagon there. So if you look at the Epcot Center, it's the same basic structure. Now, we can look at some others. We can do chemistry on these molecules. And Paul Burkett has made a very interesting molecule. One of the ways in which one can add is to add groups. Look at one pentagon and go one spoke out, and you can add phenyl groups. And in fact, if you can see it, probably not so easy, but it's got 5 legs, and it's like one of those little fossil creatures. And it's got to have an even number of groups, so it's got a hydrogen on here. And you can think of it walking. And one thing we're trying to do is to put it on a surface and see how it sits on the surface and address it. As this doesn't seem to work, I guess I can just put it away. But anyway, it's like one of those little animals that walks around. So far, Paul's only made the male of the species, but yeah, sorry. I was sure you weren't asleep, but anyway, you never know. But anyway, let me just show a couple of other things whilst we have the lights. Let's see whether this magic, we've got modern technology here. Lights, let's try this, and switch the projector off for a second. This was given to me by Sumio Iijima. With an overhead, we'd have it instantaneously, but they did say that this would work, but then maybe it won't. I'd like to show you this. Whilst we're getting this going. This is a Japanese basket, and if we, does it have to be switched off? You want to go with that old technology called overheads, all right? But they've just put something over the front, and I'd like to show you this because it has the same... Here we go. Instantaneous. All right. Let's see this structure, because Sumio Iijima gave me this, and we see, in fact, the hexagonal structure here, but we know it can't close without pentagons. And if you look, let's see whether we can see it here. We can see there a pentagonal structure. Can you see it? Hope you can see it. And next to it are hexagons. And in fact, there are 6 of these around the edge. So the ancient basket weavers in many countries discovered Euler's law. I think you can see it there. There's a 5-pointed star. Can you see it? There's a 5-point, and there's a 6. So that particular topology is very important. Let me show you another. We have the lights for a second, and show you this. This is like C70. Now, if you take 2 halves of C60 apart, that's 30 here and 30 there, and add 10 carbon atoms, and then close it off, we get C60. If we continue that, we get basically a tube of graphite. And there are many groups throughout the world, including here at Berkeley, who are now studying these nanotubes. They're fascinating. They have the strength of graphite sheet, but in tubular form. The estimates are that the tensile strength is something like 50 to 100 times that of steel. They conduct like metals. If, it's a big if, we could make this in ton quantities, these would be single molecules, stacked together. We would produce a tubular construction and get the material which probably will have a strength which is greater than anything one could ever think of. When I made one of these for the first time, I called it a Zeppelin, you know. The students had a rather ruder name for it, but let me just pass that around. It's, don't worry, just put it back together again. It's been on British Airways several times, so, you know. Okay. I think what I'd like to do, but I hate to do this, is to go back to the if I switch this off. There you go. Leave that on, maybe. Can we see the next slide? Oh. Magic. Nothing happened. I can't switch it off. Okay, that's fine. What is happening? Okay. You know, when you go around the world, you have to go, you know, give lectures in the backwoods of China and Mexico and in Berkeley. You expect to invest here, but never quite sure, because another technology really defeats me. I have to go with very simple things. Anyway, let's go on, because if we go here, I'd like to show you this, because this is one of the football teams. And on the left is Sean O'Brien, on the right is Jim Heath, the two students who really got this particular experiment going. In the middle is Bob Piero, who's got the football captain of the team. Rick Smalley on the left, who created the apparatus which was destined to discover C60. We've not yet worked out who the woman walking around the back is, but she's not come forward to claim part of the prize yet, but she probably doesn't realize. But anyway, let's go on, because here's the Sussex football team. There's Abdul Sadar, who got the mass spectrometer to work, and Jonathan Hare, who, as I say, did this fantastic experiment. Dave Walton really got me started on carbon chains. And Roger Taylor's looking very happy because he was the first guy to see that wonderful magenta color. Well, there's another football team. I'd like to show you this one because, well, one reason is it shows that I used to have hair. That's the first thing you can actually see, which is, this used to be me. Look at that, really unbelievable. Lorne Avery never had any hair, ever as far as hair. Norm Broughton and John McLeod, these are the three astronomers, and of course Takeshi Oka. We were both postdocs at NRC at the same time. And when we discovered these things in space, it got into the newspapers. This organic find will add to the origin of life controversy. And this is very interesting. A discovery by an Anglo-Canadian team of scientists disclosed on Thursday will increase the controversy amongst astronomers about the origins of the earliest primitive life forms. And it went on, and Fred Hoyle was in this article, you know, bacteria in space and all this nonsense. And then it got into a local newspaper as life's key may lie among the stars. And I put it up on the notice board, and a student wrote, "That's showbiz," underneath here. I made him do an extra year for his PhD for writing that. Anyway, I thought I'd read this out. A new discovery by Sussex University boffins could make scientists change their minds about how life began. Their theory is that the very first forms of life could have been created in outer space. And I look at this, and the people next door get this newspaper, you know, and I'm worried that they may think this is me. Most scientists believe that life emerged after the chemical reactions took place in the boiling melting point of the newly formed Earth. Myself, Dave Walton, and Colin Kirby have been working with Canadian scientists to prove that theory wrong. They have discovered proof that there are organic chemicals in, you know, look, organic in exclamation mark, some vast dust clouds between the stars. Only one simple step would be needed to change these chemicals into the building blocks of life. It's Sunday morning television in Texas, folks. You know, the chemicals were discovered thanks to Canadian work in radio astrology, okay? you know, someone did tell me that there were, what, I don't know, 1 million astrologers and 10,000 astronomers in the USA, so that gives you an idea of what the situation is. Well, in a sense, I suppose that covers a lot of what I had to say. I'd like to finish with this one, because it turns out, if I could just have the overhead for the last time, because is it possible to have the projector one more time? If I switch this on. I'm sorry for putting you this trouble. Because it turns out that in this book, so has anybody read this book? Put your hand up, or no one's going to, so someone's actually got this book. It's a fantastic book, because it turns out that in this book, we find something rather interesting. And it's this. It says, Buckyballs, she said, or formerly Buckminsterfullerene. I didn't think the pitfall of it that you'd slid down into could be very deep or a bottom very large. Its walls would surely slope inward. It's really just a pothole. Though surely the formation process was different. Possibly it's a small astrobleem. She giggled. The academic in me is really taking over, isn't it? Okay. Must be from Berkeley. Okay, splendid. Dorcas had better look to her standing as the most formidable woman in the known space. Now tell me, what the hell buckyballs are? They're produced in the vicinity of supernovae. Carbon atoms link together and form a faceted spherical molecule around a single metal atom. 60 carbon around one lanthan is common, galactically speaking. But there are other forms too. And with the molecule closed in on itself the way it is, it acts in aggregate like a fluid. In fact, it's virtually a perfect lubricant. And if we didn't have things easier to use, you'd see synthetic buckyballs on sale everywhere. A vision rose in those ruby eyes. It's thought they may even have a basic role in the origin of life on planets. That's the real final word on the whole thing. Thank you very much. Questions or comments from the audience? Yes?
Question about the two-colored fluid.
The
two-colored fluid, one magenta.
Yes.
The process was done on one and not the other.
The NMR. Yes, I'm sorry, I missed that. The magenta colored solution is C60. And the red one, the red color is stronger, is C70. And the original red solution, that red color masks C70, which is, it's a rather weak transition. And red, in fact, due to the symmetry, the C70 is lower symmetry, and therefore it turns out to have a slightly stronger spectrum. Yeah.
What's the length of the bond C60?
It's about 1.4, something like that, actually.
But it's the same for all.
More or less. The bonds aren't all the same. All the atoms are in equivalent positions. The bonds within the Pentagon are all single bonds, and slightly longer by about 5% or something like that. Slightly longer. But the bonds going out from the double bonds are slightly shorter. Probably about 139 or something to 1.44, I can't remember.
But there's only two lengths.
Yes, only two lengths. Yeah.
Did you ever meet Buckminsterfullerene?
Did I ever meet him?
Yeah.
No, I never met him. He died in 82, 3 years before we named it after C60. But I had read an article, not by him, but about some of his work, and there was a very interesting program of study that interested me. I haven't actually read any of the books, but what I had read was that he was interested in a project which interested me was in the way that cities grew. He had a lot of interest in research programs which indicate that cities should grow and be programmed so that they had within it components which were like a crystal, which would be the same wherever you were. So the components that were needed for a reasonable lifestyle were to be found in all parts of the city. And that's something that was put into practice by Brasilia Some people think not successfully, but I tell you, Brazil is darn sight better than a lot of other places in Brazil. So, that's one place that once I had to visit at one time to see how that particular experiment worked. That was an interesting thing that interested me about this book. Yeah.
Are there elements that cadmium we also have superstructures like silicon or phosphorus?
Well, silicon I don't think will do it, but boron nitride does form cage structures, and in fact, I don't think it would be easy to form a molecule like C60 out of anything, but the boron nitride, some work here in Berkeley, have made nanotubes out of boron nitride. That's a very interesting possibility. Also, molybdenum sulfide is a sheet material. In fact, the whole point about C60 is it told us something about sheet material, which we didn't realize. And that sheet material is, on a small scale, and even on a very large scale, close into a sphere. And so that's now been discovered as a fundamental thing which no one has looked at and has explained a lot of things. In particular, small carbon particles. And subparticles also are around and tend to be concentric shells of these things. So it's important. If it's done anything immediately, it's changed our perspective. And so you see tungsten sulfide, molybdenum sulfides, and other materials do form these closed cages. Yeah. No, not at all. One thing about C60 is that, I know it's got 60 carbon atoms, but in fact, people who are involved in superconductivity are experts in that area, and they found that it was superconducting somewhat to their surprise. The only comment I would make about it is, from an outsider's point of view, is that it has a lowest molecular orbital, if you are familiar with molecular orbitals. And when that is half filled, we know in physics, when a shell is half filled, they tend to have unusual behavior, and it's six-fold degenerate, and so it can take 6 electrons. When it's half filled, as it is in the case of the superconducting materials, it's K3, C60, 3 minus, and K3 plus. Then it's superconducting. I don't really know any more about that. But there are people here, I think, Professor Cohen and others can tell you more about that.
Well, so we thank Professor Kroto for a very interesting